Thank you for joining us today, everyone. This program is Wind Solutions, Perforated Wood Structural Panel Shear Walls. My name is Lori Cook. I'm the Manager of Educational Outreach here at the American Wood Council. Adam Robertson, the Manager of Codes and Standards with the Canadian Wood Council, is going to be joining us a little bit later. And this presentation is copyrighted. Here's our course description and our learning objectives. I won't spend too much time on those, as I'm assuming all of you guys saw them when you signed up. So we'll start out. We have several poll questions throughout the program today to keep you engaged. Our first one is the easiest one. There's no wrong answer. So Marcy, I'll let you go ahead and launch this first poll here.
Absolutely. Those of you that are normally here with us know how easy this one is. So we just like to get a feel for how many of each profession we have. We just value the different professions and the expertise that you all bring. So, and as usual, I wait until about 80%, which I have. So let's see, sharing. I've got about 76% engineers, 14% building code officials, 5% architects, 5% other. So welcome to everybody. And as I said, we just value all of your expertise and that you are coming to share here and just, expand your knowledge. So thank you very much.
Great. I hope we'll have something that will be useful to everyone today. We're going to talk about a lot of different things, so we'll get right into it. So I'll start with this program is going to be based on the 2015 version of our standards. So we're going to talk about the WFCM, or Wood Frame Construction Manual, and also the special design provisions for Wind and Seismic, which you'll hear me affectionately refer to as SPDWS. So we'll start by just talking about where these documents are referenced in both the IBC and IRC. We'll next get into some background information and some of the assumptions that are used in the development of these documents and in the designs that come from them. And then we will launch into some design examples. We'll start with two from the WFCM, one using the prescriptive methods, the other with the engineered methods, and then we'll do an example using the provisions from SPDWS. Adam will take it over then and show a design using the WoodWorks software that is developed by the Canadian Wood Council. He'll be using the US version of that to kind of line up with our SPDWS design. And then we'll close it out with a little bit of information on our high wind guides and how you would design shear walls using those documents. So the 2015 Wood Frame Construction Manual is referenced in both the IBC and the IRC. And if you look closely at the cover, you'll see the full title of this document is Wood Frame Construction Manual for 1 and 2 Family Dwellings. And indeed, it is geared primarily towards those types of structures, but we will talk about some options for using it in other types of structures where it can be helpful for designers as well. So you'll see here in Table 1, we have the applicability limitations of the WFCM. The building dimensions will be limited, you see here, to either a mean roof height of 33 feet or maximum number of stories would be 3 stories. In plan, your building length and width can be no more than 80 feet. If you do have a building that exceeds that, there are provisions in the WFCM for you to design the building as separate structures with interior shear walls. That's a little bit more complicated, so we're not going to get into it today, but there are provisions in there. And then when we go into our load assumptions, you'll see the gravity loads outlined here. Our floor live load is 30 to 40 PSF, which is typical for residential occupancy. You'll see the snow loads are going to be limited to 70 PSF. So sorry for those of you that are up in New England or in the mountains there where the snow loads are higher, but you'll have to use another method for those high snow load areas. We have provisions for lateral loads for both wind and seismic. Today's example, we're only going to be dealing with wind, but there are, again, provisions for seismic designs for those of you that are in seismic controlled areas. The wind speeds, you'll see, are based on the 700-year return 3-second gust. So they'll go all the way up to 195 miles per hour, and that will cover just about everything that you will see in the IBC and ASC 7 wind maps. We do have provisions for exposures B, C, and D as well. Now, I mentioned, that this is primarily a document for residential construction. However, there are some applications for single-story, slab-on-grade structures, for example, as long as it is within the limitations laid out in Table 1. So it's going to be based on the size of the structure. So, if you have small commercial or retail structures, restaurants, office buildings, things like that, this can be a really nice time saver, and it can help you design not only the lateral force resisting systems, but it also can help you design for your gravity loads. So I would encourage you, even if you don't do residential design, if you're doing small commercial structures or restaurant or retail, to take a look at the WFCM, because I think you'll get some benefit from it. So here we see the table of contents. This shows how the document is laid out. There are 3 chapters. Chapter 1 is the general information, scoping and materials and things like that. Table 1 that we looked at just a moment ago comes out of Chapter 1. Chapters 2 and 3 are parallel paths. They are different approaches that will help you design the structure. Chapter 2 is an engineered approach, whereas Chapter 3 is a prescriptive approach. But if you look at the way that the chapters are laid out, they are laid out in an identical fashion. So, and you are allowed to, for example, if you design your floors using the prescriptive approach, that does not prohibit you from designing your walls with an engineered approach. You can't mix provisions within a system, but you can use engineered or prescriptive provisions for different systems within the structure. In the WFCM, you'll see some shear capacities for shear walls and diaphragms, and those are going to be referenced from SPDWS. So the shear capacities for the WFCM are coming directly out of SPDWS. There's provisions, for adjustment factors and things like that. They are all meant to be consistent with the special design provisions for wind and seismic. For loads, for both of these documents, we are referencing ASCE 710. So the loads are coming out of ASCE 710, and then when you go into the WFCM, the shear capacities are referenced from SPDWS. SPDWS is also referenced in the 2015 IBC, much like the WFCM is. The difference between SPDWS and the Wood Frame Construction Manual is that this is a completely engineered document. It doesn't have any restrictions on the type of structures that it would apply to, so you could use it for both residential and non-residential designs. It gives you options for both ASD and LRFD designs. The Wood Frame Construction Manual only gives you options for ASD designs. So SPDWS will allow you to have the flexibility of using ASD or LRFD, whatever works for your project. There's another difference in the allowable shear wall design provisions. So in SPDWS, you'll see we have 3 different design methods for shear walls that are allowed. You have the segmented approach, or sometimes it's referred to as individual full height segments. There's a perforated approach, which we're going to be discussing today. And then SPDWS has an additional option that is not offered in the Wood Frame Construction Manual, and that is forced transfer around openings, or FTAO. So the WFCM only offers segmented and perforated shear wall designs, whereas the special design provisions for wind and seismic will give you those two options as well as the third option of force transfer around openings. So with that, I hope you guys were listening because our next poll question relates directly to that last slide.
I'm sure they were listening. So the special design provisions for wind and seismic standard includes which of the following that is not included in the WFCM? Segmented shear wall, perforated shear wall, force transfer around opening shear wall, hold downs, or, and that's, I'm sorry, I thought there was another one.
On this one. Yep.
So, all right, I've got about 30 seconds, so I'm going to go ahead and close. And let's see, 76% say force transfer around openings shear wall. And
excellent. That is the correct answer. So the special design provisions for wind and seismic offer that FTAO design option that you can't do with the WFCM. So good for you guys. All right, so next let's talk about some of the background and some of the assumptions in our designs. So I mentioned the segmented shear wall method, or individual full height segments, as it's sometimes referred to as. So in this example, you'll see we have these areas where it's highlighted as red. These are the full height segments along that wall. So each of these full height segments would have a hold downs on each end of the segment. So you'll see hold downs at each end of these larger segments. It does not require sheathing above and below our openings, so the wall doesn't need to be fully sheathed, but it does require a lot more hold downs than the perforated method, which we're going to look at here. So the perforated method assumes that we have a fully sheathed wall, but it takes those hold down requirements, and instead of having multiple hold downs throughout the length of the wall, we only have hold downs required at the ends of the wall. We're again also allowed to take advantage of the fact that we do have a fully sheathed wall, and that the sheathing above and below these openings does contribute some resistance in our shear wall. So you have a little bit of a trade-off. There's more sheathing required, but fewer hold downs than the segmented approach. So we're going to start with kicking off our design examples here with the WFCM prescriptive approach. So as I alluded to earlier, we have wind speeds allowed for 110 to 195 miles per hour. Now you'll see here in the prescriptive chapter, we only have exposures B and C. If you're in an exposure D, which is that open coastal, region, that would need to be done per chapter 2 or per the engineered chapter in the WFCM. Again, the prescriptive method does allow us to use segmented or perforated shear walls. It gives us the option of whichever one we like better. And again, there's other application limits based on the height and size of the structure. Now, when we talk about a lot of these tabulated results and tabulated approaches that are in the wood frame construction manual, those tables are all based on what we call our quote-unquote baseline wall. And that baseline wall is described here in section 3442. So the wall will be constructed with studs at 16 inches on center, and then for the exterior of the wall, we assume that we have 3/8 inch thick wood structural panels, and they would be blocked. There is a requirement that all sheathing edges be supported. So that would mean that we need to have a blocked exterior shear wall, or I'm sorry, blocked exterior side for the panels. The fastenings, we assume 8D common nails with a 6-inch on center spacing at the panel edge and a 12-inch on center spacing in the field. On the interior of the wall, we assume that we've got 1/2 inch thick gypsum wallboard sheathing. And the attachment for that is going to be those 5D cooler nails with the spacing at 7 inches on center at the panel edges and 10 inches on center in the field. And again, that does require blocking for the wood structural panel shear wall. So the edges of your wood structural panel sheathing do need to be fully supported. Additionally, this is something that was not picked up for wind in the 2015 WFCM, but I do want to make you guys aware of it because it applies to wind in the 2018. There is an adjustment required based on the aspect ratio of the full height segments. So you'll see that in WFCM we have a footnote that says that the full height segments are limited to an aspect ratio of 2:1 unless you use this 2BS/H adjustment factor. And where we apply this 2BS/H adjustment factor, we don't need to use the strength adjustment that's referred to in SPIDWIS 4342. Now, in the 2015 WFCM, again, this adjustment is taken for seismic, but not for wind. In the 2018 update, it applies to both wind and to seismic. So you'll see us use this adjustment later, but it doesn't, in the 2015 version, does not apply to wind designs. It only applies to seismic designs. When you get into the special design provisions for wind and seismic, it's applied to both wind and seismic designs. So we're going to jump into another quick poll question. This one talks about the minimum shear wall construction. This is in reference to that wood frame construction manual baseline wall that I was talking about.
Okay, so I brought it up so that you'd have a little head start while Lori was chatting. So the minimum shear walls construction consists of 3/8 inch wood structural panels on wall exterior, 8D common nails at 6 inch on center at panel edges, 8D common nails at 10 inch on center in panel field, all of the above, or answers A and B only. So, all right, I've got almost 45 seconds, so I'm going to go ahead and close. And let's see, 73% say answers A and B only. And
excellent.
All right, excellent.
That's good. That's the right one. So I'm glad you guys weren't caught up. It would have been all of the above, with the exception that the spacing in choice C is incorrect. So again, that baseline wall, we have 3/8 inch minimum wood structural panel sheathing on the exterior, but then the connections would be with 8D common nails at 6 inches on center on the panel edges and 10 inches on center in the field. So, or I'm sorry, 12 inches on center in the field. That 10 inches on center is for the spacing for the gypsum on the interior. All right, so let's go into our design examples now. And as I said, we're going to design the same wall for the first 3 examples, as well as the example that Adam is going to do. So the wall is going to look like this. It's a 40-foot long wall. You can see we've got, it's 9 feet tall. We have got 4 windows in it. They are 3 feet wide and 4.5 feet high. Our door opening is 7 feet 6 inches. And let's see, here we go. And we're only going to design the first floor shear wall. Now, when we talked about that aspect ratio limit, on the panel, the full height segments, we have to look at that 3.5 to 1 aspect ratio and make sure that all of our segments are satisfying that aspect ratio requirement. So we see that for a 9-foot tall wall, the minimum full height sheathing length that we can have that meets that SPDWS aspect ratio requirement is 2.6 feet. So all of our full height segments would satisfy the aspect ratio requirements. Oh, also, before I get too far into this example, I do want to let you guys know, for those of you that have downloaded the slides and are following along at home, when I was practicing last night, I found a math error that unfortunately carried through and affected quite a few of the calculations. So if you're following along and you notice that your numbers on your slides are different than mine, I apologize. We have, as far as I know, uploaded an updated PDF on the resource page. It does note that it is updated in red next to the link. So if you want to go ahead and download the latest version, feel free. But it just corrects that math error. The rest of the content would be identical. So again, apologies for that. But so our example, our structure, we have a 2-story structure. It is in a 160 mile/hour wind zone, exposure B. Our building dimensions, the length of the wall that we're designing is the L dimension, that's 40 feet. The length of the wall that would be perpendicular to that or into the plane of your screen would be 32 feet. We have a roof pitch of 7 and 12 and a top plate to ridge height of 9.3 feet. We saw that the wall heights were 9 feet, and then our doors and windows were 7.5 and 4 feet high, respectively. Our studs are spaced at 16 inches on center, and because I live in Virginia, everything is made of southern pine, so that's what we used in our design for this example. We're going to check our design both with and without the contribution of that interior gypsum, and we're not going to check deflections today. As I mentioned, the ASCE 7 is our reference for our design loads, so that is where we would be getting those. And I know I said that we're doing a perforated shear wall design, but the way the WFCM is set up is that we first need to go into our segmented shear wall sheathing requirements table and start there. So we go into table 317A, and you'll see this table does seem a little confusing at first, but we're going to talk through it. So we're in the 160 mile/hour column here. And what we're actually looking at is we're designing the wall that's 40 feet long. So we need to go to the building dimension that would be perpendicular to that. So for this structure, we're going to use this 32 feet as our W. And then we go here to the minimum length of full height sheathing on the wall that's perpendicular to that dimension. So to design the 40-foot long wall, we use the 32-foot dimension row. So again, I know that seems a little confusing, but if you actually read what the table is telling you, it does make sense. So with that, on our 40-foot long wall, we see that for 160 mile/hour wind speed, we're required to have 19.9 feet of full height sheathing based on segmented shear wall. Now, there's always footnotes, and of course, they're important, so we want to make sure we read them. So if you go into the footnotes for table 317A, you'll see that footnote 4 allows us to apply an adjustment factor to that 19.9. It tells us that our tabulated sheathing lengths are based on a 10-foot wall height and a 10-foot top plate to ridge height. And if you remember back in our example problem statement, we have a 9-foot wall height and a top plate to ridge height of 9.3 feet. So we need to do a double interpolation here. So we're on a first floor shear wall that is supporting a roof and one floor above it. So we're going to interpolate between the 8-foot and the 10-foot wall heights to get our value for a 9-foot wall. And then we go down to our roof pitch, where we have a roof pitch of 7 and 12. So we're in this second row here, in this second series of cells here. And we're going to interpolate between our top plate to ridge height of 5 and 10 feet for that 9.3 feet that is our actual value. So when we do this double interpolation, we get an adjustment of 0.91. So we need to carry that then into our design example. And I talked about the WFCM, that baseline wall construction. So ours is going to vary from that baseline wall. So we go into WFCM table 317D, and we're going to use an exterior sheathing of 15 32nd inch wood structural panel with 8D common nails. But instead of that baseline wall spacing of 6 inches on the edge and 12 inches in the field, we're going to have 3 inches on the edge and 12 inches in the field. The interior sheathing will be identical to the baseline wall, so it's just going to be 1/2 inch gypsum wallboard with the 5D cooler nails at 7 inches and 10 inches in the edge and field. And if you go into table 317D, you'll see we have a sheathing type adjustment factor that is applied. So this will be based on the construction of the wall and tells us how much we need to increase or decrease our sheathing, our full height sheathing, and some other things based on the construction of the wall. So, so for those of you following along at home, you'll see I've got this 19.9 highlighted here. On your presentation, that might say 19.1. Again, I apologize for the error. So you'll want to go ahead and correct that, and then all these numbers that follow along with that are based on that original calculation have also been adjusted as well. But so we start with that 19.9 that we pulled out of the table. We multiply it by our 0.6 sheathing type adjustment factor, and then we can multiply it by that 0.91 that comes out of footnote 4. So we see that our required full height sheathing length on a segmented shear wall would be 10.9 feet. Calculating that percentage of required full height sheathing, we see that 27.2% of the wall is required to have full height sheathing. So now we need to go into table 3.17E and get the perforated shear wall length adjustment factor from there. So that's another one that we need to interpolate, and we get a value of 1.78. So multiplying the required full height sheathing length for segmented shear walls by that perforated shear wall length adjustment factor, we see that we are required to have 19.3 feet of full height sheathing on that perforated shear wall. And if you go back and look at the illustration, you'll see that we're actually providing 22 feet, so we are okay. Now, if we're neglecting the contribution of the interior sheathing, but keeping the exterior construction the same, you'll see that we've got 15 32nd inch wood structural panels with 3-inch edge and 12-inch field spacing of our 8D common fasteners, but no or unrated interior sheathing. Our sheathing type adjustment factor will change. It was 0.6, now it's 0.69. But the process would be identical. We determine what our required full height sheathing of the segmented shear wall is and what percentage of the wall that is. So then we calculate the perforated shear wall length adjustment factor per table 317E. And we get a required full height sheathing length of 21.2 feet, which is again less than the 22 feet that we are provided. So we'll take a look a little more closely at the perforated shear wall full height sheathing adjustment in table 317E. So this is what the table looks like, and again, you're permitted to interpolate as necessary. Now, hold downs for segmented and perforated shear walls in the WFCM prescriptive provisions are calculated in an identical fashion. And this is because they're calculated based on the capacity of the first shear wall panel. So we've got a 9-foot high wall, and you can see that the required hold down capacity is 3,924 feet. However, we see in footnote 1 here, we need to use our sheathing type adjustment factor again from table 317D. So for our wall with the blocked gypsum interior, we divide that 3,924 by 0.6 and see that our required hold down capacity is 6,540 pounds. Without the gypsum, our sheathing type adjustment factor is 0.69, so we see again our capacity of our hold down is requiring adjustment, and we get 5,687 pounds. Now, since this is a first floor shear wall, we would need to combine it with the top floor hold down requirements. And again, this is based on that capacity of that first shear wall panel. So that's why it is identical for both segmented and perforated, because it's based on the wall capacity and not the load. And for the prescriptive chapter here, we do not have any dead load offset included. So if you would like to use that, there are provisions in the engineered chapter that we'll talk about in a moment here, or you can use SPIDWIZ. Now, for the WFCM engineered approach, we start in table 2.5b, and this is where we can calculate our diaphragm loads from the wind that would be transferred into our shear walls. So again, we're in that 160 mile per hour wind gust speed, and for a 7 and 12 roof pitch, we have again a roof span of 32 feet, right? That's the perpendicular dimension to where our wall is, to the perpendicular dimension to our wall that we're designing. And we'll interpolate to get our value for a 32-foot span, and we see that we get a value for our roof of 169 PLF. The floor is a little more straightforward. We don't have to interpolate. However, there are adjustment factors that are noted in the footnotes, and you can see that we've applied one here. So let me jump ahead. So if you look at footnote 2, you'll see again that these tabulated values throughout the wood frame construction manual all assume a 10-foot wall height. So since our wall height is only 9 feet, we can apply this adjustment factor, and we get a adjustment of 0.91. So that actually reduces our wind load on the floor to 177 PLF. So our total wind load at the top of our first floor shear wall from that diaphragm would be 346 pounds per lineal foot. You multiply that by the width of the building, which is 32 feet, and then we divide it by 2 because we're assuming that there are 2 shear walls, one on each side of the house, that will each take half of the load. So we get an applied applied shear force of 5,536 pounds. So that really is a nice time saver for calculating your wind loads. You can just pull it out of the table, and you don't need to go through a full, ASCE 7 analysis for the wind. We've already taken care of all of that nastiness for you guys. So if we go into table 317D, we'll see that we do have ASD unit shear capacities of our wall assemblies that are provided. So for our wall that we're using the contribution of the gypsum wallboard, we have an ASD unit shear capacity of 730 pounds per lineal foot. If we're neglecting the contribution of the gypsum, we see the wall has a capacity of 630 PLF. So doing the math, we see that the gypsum gives us 100 pounds per lineal foot. Footnote 2 does state that walls having aspect ratios exceeding 1.5 to 1 need to be blocked. That's for the gypsum wall board. So our exterior of our wall is required to be blocked under the wood structural panels, and then for segments where we have aspect ratios exceeding 1.5 to 1, the gypsum would also require blocking. So let's look at our capacity of our walls. We have a required capacity of 5,536 pounds. We saw that our wood structural panel gives us 630 PLF and the gypsum gives us another 100. So we get a wall capacity of 730 pounds per lineal foot. Excuse me. So dividing that by the required capacity by the allowable, we see that we need 7.6 feet of wall with the block gypsum contribution. If we're not using the gypsum, we need 8.7 feet of full height wall segments. And again, this is the segmented approach. So we're going to apply some additional factors to convert this from a segmented approach to a perforated approach. So let's go ahead and look at those. So going into table 4335 from SPDWS, we see that we get this shear capacity adjustment factor, or C sub O. And we do have two options for it. So the wood frame construction manual uses this tabulated approach. You'll see later that there is also an option for calculating this out using an equation. But we're going to use the table in this example. So again, we calculated our demand as 5,536 pounds. We saw in table 317D that our capacity is 730 PLF for the wall that has the blocked gypsum, and 630 PLF for the wall that doesn't use the gypsum contribution. If we look at the full height sheathing, we use a value called L sub I, and that L sub I is the effective full height sheathing length. So we talked about that 2BS over H adjustment that SPDWS requires, so we're going to go ahead and apply that here. So when we talk about the length of the full height segments, looking at our illustration, we have two segments around the doors that were each 5 feet wide. Those do not require any adjustment because they are within that 2 to 1 aspect ratio limitation. But those 3-foot segments that are on either side of our windows will require adjustment. So we use this 2 times B sub S being just the base dimension, which is 3 feet, divided by the height, which is 9 feet. So that's what this 2 times 3 divided by 9 is. And we multiply that 2BS over H by the actual width of the panel, which is 3 feet. So that gives us an effective full height sheathing length of 18 feet. Again, our total wall length is 40 feet. Nothing's out of the ordinary with that. So we see that our percent of full height sheathing on the wall is 45%. Going into the table here, we see that we can interpolate, and we get an interpolated C sub O factor of 0.55. So we're going to multiply that C sub O by the unit shear capacities to get our adjusted capacities. So for the wall with blocked gypsum, our adjusted capacity is 402 pounds per lineal foot, and dividing that by the demand, we see that we need 13.8 feet of full height sheathing with the block gypsum. This is less than that 18 feet that we're providing, so we're okay. Similarly, with the neglecting the contribution of the gypsum, we see that we get an adjusted capacity of 347 PLF and a required full height sheathing length of 16 feet, which is still less than the 18 feet that we're providing, so we're good to go. For the hold down design, the engineered chapter does it a little bit differently than the prescriptive chapter. You'll see we do it based on the unit shear capacity times the height. So it is, again, based on the capacity of the shear wall panel, but we calculate it out. So we have, for the wall that has the block gypsum, a hold down requirement of 6,570 pounds. For the wall without the gypsum, it's 5,670 pounds. Again, since this is a first floor shear wall, we do need to combine it with the top floor hold down requirements, and it is based on the capacity of that first shear wall panel. The primary difference that we see in Chapter 2 versus Chapter 3 is that there is language that will allow us to account for dead load offset in the overturning. So we are allowed to use up to 60% of our dead load per WFCM 224 to offset some of that overturning force. So now we'll jump into the special design provisions for wind and seismic, or SPDWS. And this is the bread and butter of our shear wall capacity table right here in Table 4.3a. But the primary difference between what we're looking at here and the values that were expressed in the wood frame construction manual is that these are nominal unit shear capacities. The ones we looked at in the WFCM were ASD capacities. So we're going to need to adjust these values to an ASD basis. So we're going to use a wall, again, we're going to stick with that 15/32 inch nominal panel thickness, and we're going to use 8D fasteners. But for the SPDWS example, instead of 3 inches on center spacing, we are going to use 4 inches on center, and you'll see why in a bit. But to adjust that to an ASD basis, we need to divide it by 2. So you'll see our ASD capacity is 533 pounds per lineal foot for this wall assembly. Similarly, we'll use the gypsum in the example. So we go in and divide the 200 pounds per lineal foot that we see in the table there by 2, and we see that the ASD capacity of our gypsum is 100 PLF. So I talked about this C sub O factor earlier, and how in the WFCM engineered chapter, we use the tabulated values for C sub O. We are also able to use SPDWS equations 435 and 436 to calculate a C sub O. And the difference between the tabulated approach and the calculated approach is that the tabulated approach assumes that every opening in that wall is the same size as your maximum opening size. So in our wall, for example, we had one great big opening at the door and then several smaller openings where we have windows. But the table assumes that all of those openings are the size of the door. Not really the most efficient approach, so if we want to squeeze a little bit more efficiency out of our design, we can sharpen our pencils and calculate this C sub O. And when we do that, we use this value A sub O, which is the actual area of the openings. We have our other values. H is just the wall height. L sub I is, again, that effective full height sheathing length that we've calculated, and then total wall length as well. And then you can see the R value here. This R is calculated using equation 436, which is displayed here on the right. And we get a C sub O of 0.78. Again, the value that we got out of the table was substantially lower. It was 0.55. And that's because it's based on an assumed opening size. when we calculate C sub O, we're able to take advantage of the fact that some of those openings are smaller. So this C sub O is based on actually how much of it is really sheathed versus an assumption of opening size. So that's why there's a difference between the two of them. So multiplying that C sub O value by our shear wall capacities, we see that for the blocked gypsum wall, we have a capacity of 494 pounds per lineal foot. So we need 11.2 feet of full height sheathing. Neglecting the contribution of the gypsum, we see we're going to need 13.3 feet of full height sheathing, and both of those values are less than the 18 feet effective that we're providing. So this design would work. So this is an illustration of what your diagram would look like. You have a fully sheathed wall, and you only have hold downs at the ends. So that's the trade-off with the perforated design method, is that you move your hold downs to the ends, and you have to sheathe the entire wall. Now about those hold downs. Now in the WFCM, I mentioned that the hold downs were sized based on the capacity of that first shear wall panel. In SPDWS, we have a different approach. You see here equation 4.3-8 gives you the required hold down capacity, and it's based on the induced shear as well as the C sub O that we calculated earlier, as well, and the L sub I, and the wall height. So for our SPDWS design, we see that we only have a required hold down capacity of 3,549 pounds. Again, remember, this is a first floor shear wall, so we do need to combine it with the top floor hold down requirements. And unlike the wood frame construction manual approach, this one is actually based on the loads. So it's not based on the shear wall capacity, it's based on how much load is actually applied to the wall. So you do need to do a little bit more number crunching, but you can get some efficiency in your design. And again, much like the WFCM engineered approach, you can account for dead load offset to help offset some of that overturning moment. And the language that allows that is in 43642. So here's our kind of summary table here that shows our required full height sheathing lengths and our required hold down capacities using those three different design methods that we discussed. The WFCM prescriptive approach is the least engineering intensive, requires the least amount of number crunching, but it's also the most restrictive in that you need to have 19.3 feet of full height sheathing. And you'll also see that for both the WFCM prescriptive and engineered approaches, our nail spacing is the very tight 3 inches on the panel edges and 12 inches in the field. If we do a little bit more number crunching using the engineered approach, we can reduce that required full height sheathing length down to 13.8 feet with the gypsum contribution, or 16 feet without. But again, we're still needing that 3 and 12 nail spacing. The hold downs for the prescriptive and the engineered are essentially the same. It's, you know, a few pounds difference here and there due to some rounding. But where you really start seeing efficiencies in your design is when you look at the SPDWS design. You'll see we've got even less required full height sheathing, only 11.2 feet, but our nail spacing, we were able to loosen it up a little bit and go to a 4 and 12 spacing. So we're able to have our nails spaced farther apart. We have less required full height sheathing. And if you look at the hold down capacity requirements, we can use a substantially smaller hold down based on that perforated shear wall approach. So with that, I'm going to hand it over to Adam, and he is going to show you guys how to design that wall using the WoodWorks program that CWC has developed.
Thanks, Lori. Appreciate that. So as Lori said, I'm going to try and give you a bit of a background on the WoodWorks software program. WoodWorks Design Office software has been around since somewhere around the mid-90s. And we have 3 different modules within the software package. The first module is the Sizer module, and Sizer does gravity design. So it can design single elements within beam mode. We can design beams and joists. Within column mode, design columns as well as stud walls. And additionally, within Sizer, we have the concept mode, whereby you can lay out an entire structure, the columns, walls, the beams, apply the gravity loads, and the software will automatically run the loads down the structure and design all the individual elements. The shear wall software, which we're going to talk about today, is responsible for the lateral design. So it can generate automatically wind and seismic loads. It will then distribute those loads through the structure using either the rigid diaphragm assumption or flexible diaphragm assumption, and then it will design those individual wall segments based on either the segmented approach or the perforated approach. The connections software, it is able to design all the fastener types that are defined in the NDS. And finally, we have the database editor, whereby you can edit the properties of individual products, add new products if you'd like. So the software, it follows the engineered approach, so it doesn't comply with the wood frame construction manual. It only complies with the SPDWS NDS and the IBC 2015 editions. So what we can do in the software as well is it's possible to import a CAD file. So we can see along the top toolbar, you sort of work from the left to the right in order to build your model and input all the variables and then run the design. So one of the first steps that we can do is we can actually import a CAD file from the architect's drawing. We can either use a PDF, an EMF file, a WMF file, or a BMP file. And it's possible to import a CAD file for each of the different levels in the structure. And then we simply use the CAD file as sort of a tracing paper, and then you lay out your shear walls over top of the CAD file. And it's possible to dimension and scale the CAD drawing during this import process. Before we start the design, it's important to go through some of the design settings to make sure that we're comfortable with all the different settings and the way the software is performing the calculations. So if we look here in the design settings page, we see on the top on the left, the software is capable of using either the all heights method or the low rise method to generate wind loads under ASC 7-10. It's possible for the user to turn on or off the deflection analysis. And what the software does by default is it performs an envelope design. So it will distribute the loads based on the rigid diaphragm assumption. It will also distribute them based on the flexible assumption. It will take the worst case for each of the different shear walls for each of those different loading assumptions and rigid flexible assumptions. As well, if we look down a little bit further, the hold down forces and the drag strip forces can either be based on the applied loads in the shear walls, or they can be based on the shear wall capacity. And on the right side of this page, we can see that the software is capable of using either the 3-term deflection equation or the 4-term deflection equation for the deflection of shear walls. And when we're developing the perforated shear wall CO factor, we can either take it from the SPDWS table or you can use the equation, and the user can define which option they'd like to do for that. And then finally, we see at the bottom on the right, it is possible to check serviceability for wind, and the user can turn that on or off and define the drift limits that they would like to check against. So the next thing that we need to do when we're building a model is we need to create blocks. And what blocks do in the structure in the model is they basically differentiate parts of the structure that are different heights. So if we had a 2-story house with a 1-story attached garage, we would need one block defined as 2 stories for the house and another attached block as 1 story for the garage. And here we can, within the blocks, we can define what our wall heights are and our floor depths as well. Once we've defined the blocks, we can then go in and we can develop our wall constructions. So the software is capable of designing the segmented shear walls as well as perforated shear walls, and it comes with a few default standard walls. But the users are also able to edit their own personal standard walls. So if you have a typical shear wall that you're often using as an exterior wall or an interior wall, you can define that as a standard wall, and you'll have that saved for all of your subsequent projects and models that you're creating in the software. If we look at the specific example that we were doing today with Lori, we can see here that we can define the exterior side of the shear wall as a structural sheathing wood panel material that's 15/32 inches in thickness, and we can define as well the types of fasteners that we're using. So in this case, for the example, we're using 8D common wire nails with the edge spacing at 4 inches on center and the field spacing at 12 inches on center. As well, the software is going to automatically select those nominal capacities of the shear walls based on the SPIDWIS table 4.3a, and it's going to automatically adjust those nominal capacities into the ASD capacities. So what we see here in this screen is the interior side of the shear wall. So we can define 1/2-inch gypsum on the interior side of our shear wall with cooler nails that are 5D with edge spacing of 7 inches on center. And finally, we can also define for our shear wall construction the framing material. We have here southern pine 2x6 lumber material that's spaced at 16 inches on center. So we can see on the bottom on the right as well, the software has a database of hold downs from the Simpson Strong Tie catalog. So the user can define a specific hold down for each end of a segmented shear wall or for each end of the perforated shear wall length. And the software is going to automatically pull the capacity of those hold downs from the catalog, and it's going to check that capacity against either the applied loads or the shear wall capacity itself for the uplift force based on the user selection. So we can see here in elevation view, the software is capable of doing segmented walls, which we see as shown in a solid filled color, a perforated wall with a double hatch, and as well we can define non-shear walls in the software too. Once we've defined our wall construction, we can then go in and we can indicate where we have openings in our shear walls. So we can see here that we can define the width of the opening, the height of the opening, the offset from the bottom of the shear wall, and the offset from the edge of the shear wall. As well, on the right side, if we have a segmented approach, we're going to need to define hold downs on each side of those openings. And so similarly, here we have selections from the Simpson Strong Tie catalog for hold downs on either side of the opening. Once we've defined the dimensions of our shear wall and the openings, we can also review the shear wall in elevation view. So here in elevation view, we see it's showing us the total length of our perforated shear wall, the total height of the shear wall, showing us our dimensions of our openings, as well as it's providing us with the aspect ratios for each of our full height shear wall segments. That's the AR value that you see, And then below that, the Li value, that's the effective perforated shear wall length for each of those full height segments using the 2B over H adjustment factor that Lori discussed. So the software is going to do all those calculations for you, the aspect ratio and the Li values for you automatically for each of the different segments along the perforated shear wall. As well, we can see that in the elevation view, the software is going to output what the exterior wall surface is and the interior wall surface that we've designed. So the exterior, the wood structural sheathing, and the interior, the gypsum board. And it's going to calculate that perforated shear wall factor, the CO factor, for us automatically. And it's going to calculate the total, the sum of all the Li lengths along the perforated shear wall. So we see here the Li, the total is 18, and the total length of our wall is the 40 feet. So the software is automatically applying all of these factors and equations from the SPDWS automatically. Once we've defined our walls and defined our openings, we can then go in and we can define a specific roof type. So in the software, we have options for a gable roof, we have a hipped roof, and we have a flat roof. We can change the direction of the ridge. We can also modify the slopes of our roof, and we can adjust the ridge elevation up or down, which will also modify the slopes. As you can see from the bottom box, we can also adjust our overhangs. And so all of these different adjustments are going to contribute to the wind load generation and the shape of our roof and how those wind loads are automatically generated. After we've developed the roof dimensions and the inputs, we go to the site information. So this is all the information related to the generation of the wind loads, the automatic generation of the wind loads. So we can see here, we can now input our basic wind speed as well as our serviceability wind speed. We've provided links where you can find those for different locations. And we can now input our exposure and our enclosure of our specific building that we're designing. In addition, the software allows you to input minimum wind loads for both your walls and your roof, and it can do calculations for speed up of wind over hills and over escarpments. On the right side, you'll see that there's an option to include the dynamic analysis for the all heights wind generation method, so that the user can either turn that on or off and input those different variables for that type of analysis. Not going to talk too much about the seismic load generation, but here we can see all of the different inputs for the automatic seismic load generation. We are using the equivalent lateral force procedure defined in ASC 7-10. So we can see here the user can input the risk category of the building. The software will automatically calculate a period for the building, but we do give the user the option to manually input a period if indeed they've gone through and performed a rational analysis to calculate a period for their specific building. On the right side, we can see here all of the spectral response acceleration values based on the specific geographic location, as well as the site class we can input here. And all these inputs are going to be combined in order to develop the base shear and the lateral load generation for the structure. This page here is the load generation screen. So the user can either generate wind loads or seismic loads, or generate both of them. We can display the loads as either line loads or as area loads. And the software also has the ability to develop components in cladding wall loads. The seismic loads we can see here for the floors, the roof, the interior walls, and the exterior walls. We need to define the self-weights of all those. And those are going to contribute to the building mass and the generation of the base shear for the building. So this screen here is a sample screenshot of the the plan view of a gable roof situation where you have an automatic wind load generation. So we can see the software is capable of developing both the windward loads as well as the leeward suction loads on a building. So I've talked about the automatic wind load generation, but in addition to the automatic wind load generation, the software is also capable of having the user manually input lateral loads. So in this situation here, we can, for our example, we can manually input a lateral load, a wind shear load of 5,500 pounds on a specific wall line. And if you look on the left in the box, we can see there's different types of loads that we can manually input: seismic loads, wind shear loads, wind component and cladding loads, and uplift loads, as well as dead loads. And if you look on the right, the elevation view, as soon as we input a lateral load manually on a specific shear wall line, the software is going to automatically make the calculation to generate the corresponding uplift force based on that lateral load. If we look at this in elevation view, we see on the top on the left is the lateral load that we've manually inputted, and the software then is going to be able to generate other loads, such as the drag strut loads. So the drag struts are responsible for dragging the forces from the one full height segment over the opening to another full height segment. And so the software is going to automatically generate all those drag strut forces, as well as the anchorage forces that you see at the bottom of the full height segments. So now we're ready to press the calculation button. So if we press the calculation button, there's several pages of output. One of the outputs is the echo of the wall construction. So we want to check to make sure that indeed we've specified the wall construction that we're expecting. So here we have our exterior surfaces, our wood structural sheathing, interior is a gypsum with a certain size of nails and certain spacings for edge nail spacing and field nail spacing. As well, at the bottom, we have our framing materials. So in our case, for the example, we have a 2x6 southern pine material of stud grade, and our spacings at 16 inches on center. With one of the tables in the output is also going to show you all of the different lengths of your perforated shear wall. So we have our total length of our perforated shear wall. We have the length of each of the individual full height segments, as well as the aspect ratios for each of those full height segments, as well as the different lengths of the openings and the heights of the openings. So this is shown in the output as a tabular format. We can also see this in a plan view format. If we look at the drawing, here we see our perforated shear wall with our applied load and the corresponding uplift force. So now we can see the shear results, and this is the important consideration that we're looking for here. So if we look at this table, starting at the left, we see this V value, which is the applied shear force, the pounds per linear foot. So this is the 306.7 value, and we have the 5,500 pounds divided by our effective length of perforated shear wall length of 18 feet. That gives us the 306.7. And then if we look over on the right-hand side of the table, we see what our allowable shear is. So for the interior gypsum, we have our allowable shear of 100 pounds per linear foot. For the exterior wood frame sheathing, we have 532 pounds per linear foot. If we combine those together, we have the 632 pounds per linear foot allowable shear. We multiply that by the perforated shear wall factor, the 0.78, and that's what's going to give us this 496, the combined the allowable shear for our perforated shear wall. And if we multiply that by our effective length of perforated shear wall of 18 feet, that's how we're getting the 8,922 pounds. The response ratio on the right is simply the allowable shear force, or the applied shear force divided by the allowable shear force. And so we can see for this specific wall, we're at about 62% capacity. So we see that we have a wall, we're at about 60% percent capacity, we can say, well, let's go back and do our analysis, but now we're not going to include the gypsum. So if we simply go back into the walls view, we look at the interior side material. We specify, instead of the gypsum there, we specify there's nothing on the interior side. And then we rerun the design again. Now we see that our wall construction is only exterior wood frame sheathing with our 2x6 studs. And if we look at our shear results, the applied force doesn't change. That's still the 5,500 pounds applied force, but we see the allowable shear has now changed, so it's been reduced. We have our exterior shear wall that's 532 times our perforated factor 0.78 is giving us the 417, and then we multiply that 417 PLF times the 18 foot of perforated shear wall length, and we get the 7,500. So now our wall is at about 70% capacity when we're not considering any contribution from the gypsum. In addition, the software can go ahead and check the hold down capacity against the hold down forces that are applied. So in this case here, we have a hold down capacity of about 5,600 pounds with an applied uplift force of about 3,500 pounds. So our hold downs are at about 60% capacity. So we can go back, we could adjust those hold downs potentially to a smaller size in order to get higher efficiency out of our hold downs. As well, the deflection is included in the software calculations. The software is going to automatically calculate the main wind force resisting system deflection, as well as the serviceability deflection. And we can see here the 4 different components to the deflection. It's calculating the bending component, the nail slip component, the shear component, as well as the hold down component. So if we add those 4 components together, that's how we're getting the total deflection for both the main wind force resisting system and the serviceability. And finally, the story drift. The software is going to take the allowable story drift that the user has defined. In this case, we've defined it as the H/500 and compare that to the maximum deflection along a shear line. So in this case here, for story drift, we're at about 90% capacity. So that, in this case, could potentially be the governing design criteria for this particular wall, would be the drift limits.
All right, so let's go ahead and take a quick poll. WoodWorks Shear Wall software can automatically generate wind and seismic loads and manually input lateral loads. Is that true or false? All right, and we're going to make this a really quick one. So 95% say true. What do you say, Adam?
Well, that's great. Everybody was listening closely. Yes, so we can automatically generate loads, or we can manually input those specific wind or seismic loads as the user sees fit if they want to generate them elsewhere outside of the program.
Great. Hello again, everybody. Thank you, Adam. That was excellent. Very good knowledge there. So we're going to wrap it up today, spending a little bit of time talking about the Wood Frame Construction Manual High Wind Guides. You'll see the cover of the one we're going to be working out of for this example here. We have developed them for wind speeds, I believe, from 115 miles per hour up to 160. In most cases, they're available for exposures B and C. And these all actually use the perforated shear wall design approach for the shear wall design, but they also have lots of provisions for designing other elements in the building. So you can actually design the entire building from your sill plate all the way up to the ridge beam using the high wind guides. These are very prescriptive in nature, so you'll see they're based on the WFCM, so you'll see the same provisions with respect to limits on the size of the structure, the mean roof height, and the maximum building dimension and plan. In addition, you're going to see some additional restrictions. The top plate to ridge height is going to be limited to 10 feet. And then your roof truss or roof rafter is going to have a maximum allowable span of 36 feet. Some additional restrictions beyond what's in the WFCM. Our openings are limited to 6 feet 8 inches. You can go up to 8 feet if you apply a 5% increase in the full height sheathing lengths in the shear wall tables we're going to look at momentarily. The aspect ratios are limited based on the wind speed. So we're going to look at the aspect ratio limits for 140 miles per hour exposure B in this example. But be aware that it does vary with the wind speed. So if you are using for example, 160 mile per hour exposure C document, you'll see that the aspect ratio of and that's of the entire structure, not of the shear wall, but of the actual structure, the length and the width. So those are going to be limited. And the buildings need to be rectangular. If you are designing a non-rectangular structure like what you see in the illustration here, you can use the inscribed method. That would be allowable. However, if you're using the separate structures method that I alluded to earlier, where you design the building as separate structures with internal shear walls, that's going to need to be designed per the wood frame construction manual. So you would not be able to do that using these high wind guides. So let's take a look at the structure we're going to design. It's similar in shape and size to our other building, but it's got some slight differences. This is actually our old WFCM house, and the wall we designed earlier was out of the new one. But this is an example house that we've used in the past, and a lot of you have probably seen it. So our wind speed on this example is 140 mile per hour exposure B. The length of the wall that we're designing is 36 feet. The length of the wall into the plane of your screen is 30 feet. Our roof pitch is 5 and 12, and our top plate to ridge height is 6.25 feet. It's a 2-story structure. Our wall heights are 8 feet, and our door height is limited to 6 feet 8 inches, so we are within that restriction. Our windows are 4 feet in height, and we have wood structural panel exterior sheathing with gable end walls. We need to calculate the aspect ratio of our structure. So you'll see here in Figure 4 in the High Wind Guide document, we have an aspect ratio limit of up to 2.75. Our building is 1.2, so we're all right. You'll also see limits on the wall heights. I did mention that this document would be limited to 10-foot wall heights, and you might notice that you'll see a lot of places where it says 9 feet 9 inches. If you add 1.5 inches for the sill plate and then another 1.5 inches for the top plate, that will take you up to a 10-foot wall. So our wall heights are 8 feet, so we're all right in our design here. I just wanted to show this to show that there's a lot of really nice illustrations in this document, and can help you, resolve not only, shear and lateral, but also uplift designs. And in these illustrations, it will point you to exactly what table you need to go to get, the values for connections or material sizing or things like that. So if you do a lot of residential design in high wind areas, this can be a real big time saver, and you'll see how very simple it is to use the document. Now this document, as I alluded to, it assumes that we have a fully sheathed wall, so it is a perforated shear wall, and we only have hold downs at the ends as is required in a perforated shear wall design. Going into Table 13, so this is designing the shear wall for the long dimension of the building, the 36-foot long wall. We're going to first look at we're going to design the second and the first floor walls because it's so quick using these that I have time to go through everything. So if we look at our second floor wall, it's supporting just the roof and ceiling above it. And we have a 6-inch edge spacing and a 12-inch field spacing of our 8D common fasteners. And for an aspect ratio of 1.2, we're going to interpolate to see what our percent of full height sheathing is required on the wall. Interpolating, we see that we need 13 feet of full height sheathing. We've provided 23.5 feet, and you can verify that in the illustration. And our hold down capacity is just coming out of this cell here, so it's 4,360 pounds. Very straightforward. Now let's go ahead and do the first floor design. So our aspect ratio is again 1.2. So if we interpolate, we see that we need 59.8% of full height sheathing using this 6-inch edge spacing and 12-inch field spacing. That is going to equal 21.5 feet of full height sheathing, which is in excess of the 21 feet that we've provided. So this design's not going to work. It's no good. If we go to a slightly tighter nail spacing using that 4-inch edge spacing and 12-inch field spacing, we see that we can make it work because when we interpolate, we see we need 46.8% of full height sheathing, which is 16.9 feet, which will meet our requirements of the 21 feet that we've provided. We have a slightly higher required hold down capacity. It's 5,900 pounds. So combining the first floor and second floor hold down requirements, we see that our hold down capacity on the first floor is 10,260 pounds. All right, let's design our gable end. We did not have an illustration of the gable end in this case, so what we're going to do is just provide the maximum amount of openings we can have in this design. So for the second floor, we're going to assume 6-inch edge spacing and 12-inch field spacing everywhere. And again, just interpolating between the 1 and 1.25 aspect ratios based on our aspect ratio of 1.2, we see that we have to provide a full height sheathing of 14.2 feet. That means that on our 30-foot wall, we're allowed to have 15.8 feet of openings. And the hold down capacity is again 4,360 feet. Following the same process for the first floor, we see that we're going to use that 6 and 12 spacings again. Our required full height sheathing is 75% of the wall, or 22.5 feet. So our maximum amount of openings on the first floor of our gable end is 7.5 feet. Hold down capacity would be 4,360 again. So we'll combine it with that first floor hold down requirement, and we get a hold down requirement capacity requirement of 8,720 feet. So we're going to specify the larger hold down capacity obviously is going to control. So we'll need a hold down of 10,000 with a capacity of 10,260 pounds at all 4 corners of our structure. And in this illustration, you can see that how it's detailed such that we only need to include 1 hold down at the corner, but we do need to provide shear transfer between the walls. So you see this illustration on the right here showing these 16D common nails at 6 inches on center. That's to allow for shear transfer between the walls so that you have a continuous load path to that hold down. So we've got one more poll that I'm going to ask Marcy to go through just pretty quickly since we're running short on time here.
Absolutely. Okay, yes. The 2015 WFCM uses shear wall design capacities from which of the following? Is that 2015 International Building Code, 2015 SPIDWIS, ASCE 710, or none of the above? All right. right. And I've got a lot of folks here in 30 seconds. So 56% say 2015 SPDWS and a smattering everywhere else. So what do you say?
We stumped some of you guys on this one. Excellent. The answer is, the majority is correct. It is the 2015 SPDWS. So the shear wall design capacities are from SPDWS. The loads are from ASCE 710. So good on you guys. That one was, I had mentioned it very early in the presentation, so you guys were paying attention. So that is going to close out the AIA accredited portion of our course. I do want to make you guys all aware that Canadian Wood Council does offer a discount to AWC design professional members on the WoodWorks program. And again, this is the US version that's designed for the US standards and codes, so you wouldn't need to worry about it being for a different set of standards just because our friends in Canada produced it. But it is available at a discount for AWC members.
Okay, thank you, Adam and Lori, for providing a great webinar for us. And we did have some really good questions that came in. One question has to do with, could you elaborate on the High Wind Guides and where are they located on our website, and some significance between the various versions of the High Wind Guide?
Yeah, all right. So here, let me just get my AWC. So if you go on our website here, I'll start back at the beginning. So we have our codes and standards button there. You just click on that and then go into our publications. So when the publications page pops up here, all right, there we go, there it is. You'll see we've got the wood frame construction manual. Now we don't have the 2018 High Wind Guides. They're not completed just yet, so we talked about 2015 today. So if you go on the WFCM page and scroll down, you'll see the High Wind Guides are offered. They're free downloads, and we offer them for 115 mile per hour up to 160. You'll see the 160 mile per hour exposure, we don't have an exposure B, and that is primarily because most of the places where you see 160 mile per hour wind speeds are in Florida. I did learn in our earlier presentation that there's actually some in Texas on the Gulf Coast too, but Florida beat you guys to it, so we followed their lead on this one. In the state of Florida, there's a requirement that if you are in 160 mile per hour wind speed or greater, you're required to design it as an exposure C. So bearing that in mind, we opted not to offer 160 mile per hour exposure B wind guide because they're just really wouldn't be that much demand for it.
Great.
So
good information. And those are all free to download from our website.
Yes, they're all free. You can download the PDFs right off our website here.
Okay, and another question came in related to the designing of shear walls with gypsum and R factor and all that.
Oh yeah. I always do this to those engineers out on the West Coast, don't I? I scare a few people. Let me get this slide up here. I think, yeah, this is the one I will show. So we did our designs today were wind designs, and for those of you that are in primarily seismic driven areas, you might be aware that it's a little different with combining the capacities of the interior and the exterior sheathing. So when you are in a wind controlled design, you are permitted to combine the capacity of the wood structural panel and the gypsum interior. Again, this is only for wind designs, and that's because we don't have a response modification coefficient in a wind design per ASCE 7. That's going to be only for seismic designs. So I always do this to those of you out on the West Coast that are, you know, sometimes you might still just be waking up or something. So this is a wind example, so we don't have to worry about response modification coefficients or anything like that.
I hope they're not just waking up. It's about noon here.
Well, this morning, the one that I gave this morning, I think
Oh, okay.
they had their coffee yet. But
Okay, here's another question related to blocking versus unblocking, and you're on the right slide there, I believe. Could you explain that a little bit? What's the minimum requirements? And
right. So, so you'll see in this table here, the gray cell up at the top here describes the exterior wall sheathing. So you will see that it is required to be blocked per this description of the construction. Your gypsum is allowed to be unblocked in certain situations. So if you look at footnote 2, if your aspect ratio of your wall is less than 1.5 to 1, your gypsum wallboard can be unblocked. However, if your aspect ratio exceeds that, you do need to block the gypsum as well. Right. And in that baseline wall that we talked about in 3442, I think it was, that also stated that it assumed that all panel edges were supported with framing. So that means it's either, you know, the structural framing, your wall studs, or some sort of blocking that supports the edges.
Correct. And that's good feedback. Also, that this table is not showing the nailing for the baseline shear wall. This is a truncated vision of the table, right? Yeah. So the baseline would be at 6 inches on center edge nailing.
Right.
Okay, another question related to hold downs and the inclusion of dead loads.
Yeah.
How do you treat that?
So I did mention in Chapter 2, in the engineered approach of the wood frame construction manual, you are allowed to use some of the dead load to offset the overturning moment. You are limited to no more than 60% of that dead load, however. And again, that's an ASD design that you're using in the wood frame construction manual. So, you know, for LRFD, if you're doing an LRFD design, you'd be using SPIDWIZ. SPIDWIZ does have language to allow dead load offset. I don't know off the top of my head what section that's in, but it is included in SPIDWIZ as well.
Yeah, I can't remember what section either. Another question came in regarding the type of wood structural panel. Is it plywood? Is it OSB when it mentions wood structural panel?
It can be either plywood or OSB. They would be considered to be structurally equivalent in this case. So it's based on the nominal thickness. So that, you know, 3/8, 7/16, 15 32nds. You can use plywood. You can use OSB. Either would be acceptable, obviously, as long as it's an APA or TICO rated sheathing. Right.
Okay, and then that was good. Then let's see, related to the use of the requirement of 3x3 washers, where would one go to find that information?
That's in, so the 3x3 plate washer requirement comes out of SPIDWIZ. And let me see.
And
so
that's all I.
Yeah, there are some exceptions to it. Let me see if I have my SPIDWIZ in front of me here. Yeah.
It is required per this.
Yes, there are some exceptions where you do not need to use the 3x3 plate washers, right, related to, you know, if it's a lower capacity wall, and I think there may be some other. I think it's generally related to the capacity.
Yeah, I should have prefaced it. Would you look in the wood frame construction manual or the wind?
Right, no, that would not be in the WFCM. You'd have to go to SPIDWIZ to learn what the nuances of that one are.
And I just pulled up the section. It's 4.3.6.4.3.
I did not know that one off the top of my head.
I know. Okay, so let's see. Let's go to Adam then for a few questions on that. on his part of the presentation. Adam, are you, is your microphone on?
Yeah, I'm here. Hopefully you can hear me loud and clear.
Yep, I can hear you. And one question that came in is, what is WoodWorks available for Windows, or what versions are there available as far as the system, computer system, operating system?
So at the moment now, we only have the version of WoodWorks available for the PC. We have had some requests in the past for an Apple-based version, but at the moment we just haven't had the critical mass to be able to justify the development. But if indeed there are users out there that have a need for the WoodWorks software on the Apple system, please do send us an email, let us know, because we're always reevaluating the needs of the users. And if indeed we feel that there's a need out there for an Apple system, then we would go that direction.
Great. Another question came in related to the hold downs and the use of Simpson Strong Tie. Are there other hardwares, types, manufacturers available in the system? And go ahead.
Yeah, so it's a good question. And at present, we only have the Simpson products that are automatically in the system. So the software will automatically associate the capacities with the different hold downs and the other properties. But there is a hold down database in the software, and the user can actually go in and create a hold down with any capacity and any different properties that they so choose. So if there is another manufacturer out there that is typically being used by certain designers, then they can go in and they can input those properties and then use those manually inputted hold downs for their design and their analysis using the Shear software.
Great. Another question came in regarding using CAD drawings and locating of shear wall openings, and how does that interact with the WoodWorks software?
Yeah, it's a good question, and the CAD drawings, essentially what the CAD drawings are a tracing paper. So the CAD drawing, the software is not going to recognize where walls are, where openings are on the CAD drawing. It's simply a tracing paper that the user can then draw their shear walls and their openings to match or to overlay the CAD drawing. And that's the extent right now of the interaction between the CAD and the software. So it doesn't actually read to the level of where openings are and automatically apply them in the WoodWorks software.
Okay. Another question related to, does the software have the capability of doing force transfer around opening shear walls?
Yeah, no, and something that I didn't mention, but Lori had talked about the 3 different methods. So at present, we're on version 11 of the WoodWorks software, and version 11, it has the capability of doing the segmented shear wall approach or the perforated approach. But we are developing version 12, which is scheduled to be released in early next year. And version 12 will actually incorporate the force transfer around openings method as well. So we're in the final stages of testing the calculations. And if you're interested in test driving it, it should be available for anyone to use in the new year, hopefully January, February timeframe.
And did you mention what method?
Yeah, in version 12, it would be the Diekman method that we're using in the force transfer around openings. As well, we have aligned our calculations with the APA calculator on the APA website, so users can have confidence that indeed the software is doing the calculations as per APA has outlined as well.
Great. Okay, another question is, will the software be incorporating the 2018 NDS? And in addition to that, what about cross-laminated timber?
Yeah, so the new version 12, which is coming out early next year, it will comply with the 2018 NDS, the 2018 SPDWS, and the 2018 IBC. It will also incorporate CLT, but only for gravity design. So the sizer components of the WoodWorks software will have CLT gravity design in the next version coming out next year, covered under NDS 2018.
Great. And we are looking into doing an actual webinar for floor design and wall designs for gravity design in 2019. That's excellent. So I have a question for both you and Lori, and it has to do with in-plane and uplift shear walls. Lori, do you want to take this? Is that covered in the wood frame construction manual?
Oh, I believe it is. But I do not have the reference on that one
yeah, I
available.
don't remember the reference number.
Yeah.
And what about the software, the WoodWorks software? Can it do combined in-plane and uplift resistance of the shear wall?
So the way that the software works is that it automatically generates lateral wind loads, but it doesn't automatically generate uplift wind loads. So the user needs to manually input those uplift wind loads, and therefore we don't necessarily have the capability at the moment to model them with the combined shear and uplift for the shear wall.
All right. We're talking about, I should have clarified, we're talking about the shear wall resisting uplift as opposed to hold downs resisting uplift. And I believe we're going to be doing a webinar on this next year. So something to come up next year to keep an eye out for. Okay, any last comments that Lori or Adam you'd like to make on the webinar?
I'd just like to thank everybody for joining us today, and thanks for sticking with us through the questions.
Yeah, thanks everyone. Thanks Marcy and Michelle as well for the organization.